Okay, now we are arriving in the core of the training program with the presentation of LPI, which is a software system to manipulate L systems. And in this part, we are going to see the basic concepts about this type of language and make a number of practicals to start manipulating a bit these elements. So as we said before, we have L systems. We would like to have a computer system in order to manipulate this, compute in an automatic manner the derivations, define the languages, the rules, the system of rules, define the actions, and in a way that makes it really flexible and easy for the user to construct complex accumulation of rules and accumulation of string elements. I repeat this because I didn't insist so much before on that. L systems are specific systems that are close to Chomsky grammars, which are the grammars of the natural language, but with a very important and key difference is that these rules, they will apply all at a time on the string to make the derivation. What important thing to remember is that you start with a valid organism. So assume that this is the state of a valid organism. You apply the rules once to all the string symbols, all in parallel, and you obtain, this is the idea, you obtain a valid state, a new valid state of your system. So the notion of parallelism, the fact that you apply the rules in a parallel way, is key to the notion of L systems, as opposed to Chomsky grammars. In order to handle this in an automatic manner, people have developed through the years a number of computer languages, exactly similar to what you can find in Python or in C language or C++, Java. So the first language that has been provided was CPFG by Przemek Przinkiewicz in Canada. He was not in, yes, I think it was in Canada. And then there are a number of other languages that have been developed with different peculiarities to code this notion of L system in a computer language. And the one that we have developed in my group some years ago was developed by Frédéric Boudon, and it's called LPI, and this is the language on which we are going to work. So the pioneering work was carried out by Przemek Przinkiewicz and his group in the University of Calgary. And originally, the language was coming like this, and you had a homemade language that is called CPFG. I didn't write it on the screen. And this language made it possible to manipulate and to give tools to manipulate L systems in an easy and compact manner. And you see that already at that time, you could make very beautiful rendering of plants with these languages. And all this was described in a book that is a famous book on using L system for modeling plants that was written together with Aristide Lindenmayer, and that was published in the year 90. Okay, so this was the pioneering work. And then Przemek Przinkiewicz continued to work on these L systems throughout this career, still at the University of Calgary, and developed a lot of concepts and notions that actually, most of them we are going to have, well, not most of them, but most of what I'm going to present is coming from his group and was introduced by their work on the definition and development of L systems for the modeling of plants. One thing that I didn't say is that L system could be used, but we discussed this during the pause. You could use L system to model many other things than plants. As soon as something comes in a branching structure, you may think to use L system, and it would be equally good or not good to model the system. Other systems you can find. This is one by Winfried Kurt, and the difference with the other language is that this is made on the top of Java language, so it inherits all the specificities of the Java language. And some people that are very keen on using Java language like very much this language, and it is well spread in many groups in Europe. This GrowGra platform or GrowImp platform. I never know exactly what is the difference. And the language is called XL. So the language to program the rules and make the derivations. And finally, so I just took a couple of well-known languages that have been written for L systems. There are others, and this one is the one on which we are going to work. It's the LPy language, and the peculiarity of the LPy language is to be based on the Python language, which is a well-known and very used language nowadays for many script development, in particular in data science. And this is why we actually chose to develop this language in Python at the origin. And it makes it possible to, exactly in the same way as the previous language, to manipulate the L systems and to create 3D objects corresponding to what you have created. So we will speak a lot of this LPy system during this session. You can install it in a couple of lines of code in your terminal. So this is using the Conda installation facilities. So you can install by using this Conda line. And then you launch the software by typing LPy. And this should open a window that is your programming window on which you can manipulate the whole system. And then if you want to access the doc, there are a number of places where you can find documentation. At the moment, there is no full documentation about the system, and this is one of the reasons why I'm doing this session now, is to, in a way, circumvent the problem and then give at least some more insights from what is already available on the web. Okay. So now, you have launched on your computer the program. It should come in this way, where you have a main window here where you can program, write your different programs. Here there are windows where you have your console and the graphical utilities. So for the moment, probably you don't have this one. And then you have panels here. You can click on these things. You can have color maps, scalar place where you can manipulate parameters. You have configuration, and so these are tuning parameters for the execution of the system. And when you click on the Run button here at the top, and you have some program here, you can obtain a window, a graphical window in 3 dimensions, where you see the plant that would correspond to the execution of the program. Okay? I propose that we try to make a hello world in LPy. So actually, when you type in new, you go in the file. Sorry, in the platform it is called. I don't have it's probably file new, something like this.
Or
yeah.
new, just
or new here, yeah. So you get empty frame for entering LPy command, and what you can try to do is type in the following. Sorry. You can type in the following commands, like underscore these things. Type in exactly the characters with capital letters, everything as you as it should be. And then you type in this line here. Okay, so this is what I consider to be the hello world in LPy. So you have the axiom, you have a production that is written here, only one rule and not many. You could have many. And you have a derivation length, which is the number of times you want to apply the derivation rule when you are going to run the system. Okay? So if you type this in your computer, or copy and paste, or drag and drop the file, you will be able to see this in the editing part of your editor. And then you run the system, and then what you should get is this type of result. So just one at a time. I just displayed all the different steps. If you go step by step, you click on step, you get this. You click on step, you get this. You click on step, you get this. And altogether, you will have the different outputs of the different derivations of your system. Okay. What is interesting is that I call this hello world in L system because you already have something a bit complicated here, where the rule is recursive. You see that the f is decomposed or is producing a f several times. So this will repeat the rule again and again and again. And this is why you have the impression that the system sort of repeats itself in some way. So we won't enter into the description of this. We will go later to that. But you see that the rules have a very important ability, which is to be recursive. And the recursivity of the rules are at the basis of the construction of plants. If you think, a meristem, according to what we said this morning, a meristem is going to produce organs that can themselves be meristems. So there is this notion of recursion in the construction of plants.
Can we see the string?
And you can see the string, yes. You can type in your, if you tap L string here, in the terminal window, if you tap L string all in small letters, you would have the L string correct. So for instance, if you type rewind, which gets to the axiom, and then you type L string, then what you see is the axiom interpreted by the L system as an actual tree, as we explained this morning. You see that the vocabulary that we introduced this morning was a bit important. Is everybody okay? Did you manage?
Yes.
Okay.
The string is awful.
And the final string is super big because each element of this string would correspond to a small segment in this fractal. Okay. So this is why it's. But on the other hand, this is the beauty of the stuff. We don't need to take so much attention to the complexity of the system. The system will take care about this in itself. We will come back also probably to this. You see that an extremely simple rule is able to produce a rather complex structure, at least with a massive amount of elements. And this is the possibility to amplify the data according to a system of rule is one of the key notions behind the notion of L system. So my original data is this one. And what I obtain here is a string that contains probably thousands of elements. I mean, if you augment this number here, 5, to 6, it will grow exponentially. So the number of elements that you can obtain here, just by changing this, from this, and by changing this number, can grow really exponentially. And this is called data amplification. Okay? So the rules are local instructions that will amplify your data and that probably can produce extremely complex shapes. Okay? Okay, so now that you have your different windows on your screen, you can go to the help and see the help card. And you see in this system all the instructions that are available within the LPI system. And you have an explanation of a large part of these instructions on the web at this following link. One key notion behind the L system is the notion of turtle interpretation, turtle geometry. So the turtle geometry is what makes it possible for the system to read a string and to transform this string into a geometry. Okay? There is no clear link between what we call the string this morning, that has potentially no meaning, and the actual fact that you can interpret a string as being a geometric object. So how do you make this mapping? This is according to the turtle geometry. So turtle geometry comes from a formal language developed in the end of the 60s at the MIT, and by people that introduced this notion of logo turtle. And this idea of turtle geometry actually corresponds to indicating geometric movement, geometric primitives in the context of the previous frame that you just constructed. So this is only local geometry. And this is the reason why it is so powerful. So we will review a bit of this. Imagine that you have a turtle, and that this turtle may obey some rule according to what she's reading. So if she reads an F, she will move forward by 1 unit, 1 step. If she reads a plus, she will turn, I think this is left, it's counterclockwise. She will turn like this by some defined angle. If she reads a minus, she will turn the opposite way. And there are a number of instructions that you can give to the turtle, and that will make it move. So, for instance, if I start from a certain position, and I read the string F, okay, F for forward, she's pointing in the direction of the H for head, so she's heading in this direction, and the H originally is the red arrow, is pointing upwards. So if I say F, she will go upwards in the direction in this direction, and create one path element that will be represented here by a cylinder. Okay, and then if I continue, I can give, using this vocabulary, I can give a string of instructions that will make the turtle wander around in the space according to what she reads in the instructions, one symbol after the other. Okay? So if I read this, I will go upwards, then plus means turning left, twice going one step forward, then turning left, etc. Okay? You can do this in 3 dimensions. So in 3 dimensions, you need more instructions to turn not only left and right, but to turn also in this way and backward and forward, and also to turn in this direction. So you have different symbols to say that you are going to turn in the different directions of space, which makes it possible to make paths in 3 dimensions. One extremely important notion is the HLU frame for head, left, and up, which is the turtle frame. So the space frame that you have on your system is the frame that is defined by the system for you, and the X is coming towards you, the Y is on the right, and the Z is going upwards. And according to this, the turtle is not exactly in the same position. It's in the position where the H is the new X, let's say. The L is so H is like this. H left is my left hand side, and up is upward corresponding to me. And this is a direct frame. Okay? So what you need, it's not so much important to remember this sometimes, but it's very important to keep track of where is your turtle. To help in this, in your hello world, you can type in your axiom, you can type, for instance, at the beginning of the string, you can type frame with a capital F, like this. And then you have the rest of the axiom here. And then you run the system. Yes, and then you can get a bit. If you want to reduce the frame size, this is important actually because you will reuse this. If you want to reduce, you put 0.1. This will reduce your frame. And if you want to reduce the thickness of the arrows, you put underscore and a certain value that will give the thickness of the system. So this is for you to manipulate the frame instruction quite easily so that you can really keep track of the position of the turtle. So this is the turtle actually. Huh? Okay, and now we can go to example number 1. And then for this, you go to the list of files that I gave you. Take example number 1 and drag and drop in the script window. And then this is showing how with the turtle you can draw a triangle or something a bit more complex like an hexagon or
What is the meaning of underscore in
yes, this means the thickness of the line. So the turtle will draw a line with a certain thickness. By default, there is a certain thickness that is defined. And if you want to change this default, you need to indicate this.
Special function or it's internal function?
Yes, it's an internal function. Do not hesitate if you don't understand things. At the beginning, you will ask this type of question. Don't worry, because very rapidly this will be clarified.
And
so
we can have underscore anywhere in the string.
And you can have underscore anywhere in this. Actually, each instruction that we're going, and the frame as well. Each instruction that we are going to present could be used at any moment during the turtle interpretation. And what you need to realize is that this instruction will take place at the place where the turtle is currently, with respect to the current position of the turtle. So if I say move forward of 1 step, I do this. If I say move forward of 1 step, I keep from my new position and then I move forward of 1 step. So I'm always moving my reference frame with me. Okay? Okay? Okay. So you can play with the example just a bit. Let's take a couple of minutes on this. You can change the width and the color. So width would be by using the underscore, and you see that if you change the width at any moment you will see that the turtle will take into account your order at the moment where you ask the order. And for the color, there is an instruction that is comma or colon. And then you can put a number here, and the number refers to you go in the color map that is on the left. And if, for instance, you have the same color as me, this should be 3 should be red. So if you put comma in the string here, with a 3, then you would see the color of your cylinders, they start to become red.
Does it matter if it's previous or after? It's the beginning of the string or after at the end of the string?
it will take effect from the moment you give the command to the rest.
Okay, so if I want to make all the shape as red, I have to make
To put in the beginning. So remember, we are in the context of reading strings. So to interpret your string, we read the string and then interpret the elements one after the other in the order of the string. Okay? Are you ready? Okay. So it's easy to increment the number of edges of the polygons and things like this. Okay? Now, we can go to this spiral example. So it's example 1b. And you see that if I want to make this spiral, the segment length will augment throughout time. If I use a naive way to do this, I would write a string like this one that I wrote for you in the example. That is s of 1 plus f of 2 plus f of 3, and it's a bit tedious to do this. So one way to circumvent the problem is to use production rules. And the production rules will make it possible to automatize the procedure. So if you start with your word that consists of A1, A2, AN, and then with a set of production rules, you make the derivation. And at the beginning, I remind you that you have the initial string, which is called the axiom in the L system terminology. And then you get the derivation. The kth element is called the kth derivation, which is a L string. And then in the end, you have your after application of the derivation a certain number of times, you get the final result, which is a L string, and that is displayed on the screen. So one exercise would be: can you change? Yes. Can you change this here? What sort of production rule would be required in order to simplify this expression and just make it appear like a production rule applied to an axiom? So can you imagine this? And we can try to make the exercise together.
You did an example with a x, y, t, and then what we need here is just to specify a single variable, which will be x.
Yes.
And,
so f of x.
Yes, and and the how to say the production of the rule will consist to find f and increment x by 1.
Yes. Okay, so f of x would become
F of x plus 1.
f of x plus 1.
F of x. And f of x.
Un peu plus fort. What do you suggest?
F of x plus 1.
F of x?
No.
Okay. So if you apply this to an axiom, let's say the axiom is f of 0. I apply this, x will take the value 0. So I will have f of 1, f of 0. And then?
And you need a plus also.
So this one, yes. So this one will take the value after if I make a second derivation. F of 1 will become f of 2, f of 1. Okay, so this is for f of 1. And then f of 0 will remain f of 0. So it's almost there. Okay, so there is a plus here, so which will make a plus here. Is that the right way? So 90 degrees, so it should be, instead of plus, should be plus 90 degrees to indicate the right angle. Oh, it's not, sorry. No, it's not 90 degrees. You turn by, probably 60 degrees here. Okay? But you see that the order, my string is f of 1, f of plus f of 2, and here what I am going to get is f of 2 plus f of 1 plus f of 0. Okay, so try this now. Did you try this on your computer to see whether it works?
And what do we put as axiom?
An axiom would be f of 0. Ah, sorry. Okay, maybe. So you need to go for the rule here. You need to go in the production rule, in the production part, not in the axiom. Okay. So.
It doesn't say.
Just exactly, f of 0 doesn't stay f of 0 because it becomes f of 1, f of 0. So in order to write this properly, you need to write a of x sorry. Ah, c'est fini ce truc. And A won't be interpretable by the turtle, so it will be skipped. So you can try this. So if I try this on f of 0, on a of 0 in the beginning, because I need to have a module that is interpretable. So it will create first time f of 0 plus 60 a of 1. Then the next time it will the f of 0. This is a rule by default. If nothing is said about the module, it will be rewritten in the same way. So f0 will keep f0. Plus 60 is not derived in the rule, so it will keep plus 60. And a of 1 will become f of 1 plus 60 a of 2. Which means that I have f of 0 plus 60, f of 1 plus 60, f of 2, and etc.
Would you have another 60 before a of 2?
Sorry?
Another 60 degrees because we have 60.
60, f. So which one? Here?
Yes. Another one because we have a 60 before a of 1.
A 60 before a of 1, yes. So a of 1 will be rewritten as this. So it will be, okay. So this is the part a of 0. Then the part a of 1 will become this. Okay? So did you try this?
So the axiom is F0 is still F0.
Yes?
Okay. And the production.
No, axiom is A0.
A0.
So first derivation is this one.
Yes.
Okay? And A1. So it's applying this with x equals 0.
Okay. Yeah. And
Second-
we don't distribute the 60 to all
No,
the terms of
No. It's really straight rewriting.
Okay. Yeah.
So I mean, and it's why it's difficult to think in this way, because you are not used. I mean, we are not used to think in this way. Yes, exactly. So think really as basically as rewriting, straight. Is that okay with everybody? So, which means that the rule is this one. But, so it's a number of characters. It's at least half of it. But using, if I want to augment the spiral here, I would need to rewrite this many times. It will be super. Now you just need to change the derivation length of the L string. And you keep the only simple rule here, this one. And you see already another thing is that it starts to be a bit complicated when you are not used to think in terms of recursivity. Because here what we have is a recursive rule where a symbol is rewriting itself. And the recursion is on the right here. So it's a bit, I mean, you need to get acquainted with this. You need to get familiar with this way of thinking. And the more you will get familiar, the more it will be easy to write your own programs. But actually plants are, I can read this as this plant apex, produce internode, turn a bit, and produce the apex. And actually what you see is a spiral that could be a liana that would
Non, juste, j'ai réussi à faire quoi sans A.
sans A, okay. Which is possible as well. Yeah. Okay. So we move on to the next thing. So it's a general strategy, and we can get this strategy. So actually, this was the type of example that I was showing in this slide, where you see that you write the apex, you have a forward step, then you turn, and then you have the apex that is recursively produced, and then we apply this rule. What you see is that the derivation will augment the number of f plus progressively, incrementally, as you make the derivation. Using this idea, you could think of drawing a circle in this way. So would you like to try? And I think this is one example. This is this example, example number 2, where you can reuse this recursive way of producing shapes, but not to make a circle and not a spiral, and see what are the constraints of making this. So again, you can take a couple of minutes. And then you are almost in the position to simulate the development of Annabena as I was presenting in the morning. Okay, now we can come back to the example where we use parameters. As you remember, because now we use parameters, but we didn't introduce really how this works. I just remind you that you may have a L system given by the vocabulary and the rule, the different productions. Sorry, the vocabulary. The different elements of the vocabulary will have parameters, which is new. We introduced this in the presentation before, but it's a bit new. And now you can give parameters, any number of parameters to your modules. And this will make it possible to make computations based on these parameters. And define rules that will make use of these parameters. As we said before, there will be a matching mechanism between the S string and the rule when you want to apply the C and the CZ and the A. And when you will apply, for instance, to A00, you will apply A of X and T. You can do this provided that X becomes 0 and Y becomes 0. Okay? So keep this in mind because this will be extremely useful and used in the following. And then we can revisit what we did with the fractal example, with the von Core curve. In this example, the L system was a set of symbols, an axiom, and a rule, and the rule is defined here. So what occurred when we did the derivations, we started with an axiom f of 1, and then we applied the rule. And when I just remind you that when I apply the rule, I can apply the rule to this. I can match this, the left-hand side and this one, provided that I give the value 1 to x, which means that automatically when I replace f of 1 by the right-hand side, x will take the value of 1. And then what occurs is that in the derivation, you have the rewriting of the f1 that becomes f of 1/3, etc.
But it should be 90 degrees, the plus or minus?
No, 60.
60 is the default?
60 is the default, yes.
Okay.
Yes. You need, yeah, I didn't mention, but 60 is the default.
And the double minus word?
And double, just think, I mean, you need to forget about algebra here.
Okay.
It's only characters.
Okay.
The characters are, it's characters.
So it's
How
plus two character?
exactly.
Okay.
And you can see even instead of characters, you can see these elements as modules. Actually, this is the term that is used in L system vocabulary. This is a module. This is a module. This is a module. This one is a module, and this one is another module. Okay? Except that I didn't give the parameters for these modules. You may have sometimes modules that are names. In order to do this, you need to declare before the axiom. You need to declare the fact that I don't know, dog is a module, and then you would write something like you can try. You would write something like module dog. And this adds the module dog to your system. If you have parameters, you would put dog of x and y. Okay? We'll make use also of this. And then if I rewrite, then I make the second derivation. Each of the elements, instead of f of 1, now I have f of 1/3. So if I apply the rule, it will be 1/3 of 1/3. It will be 1/9 for each of the elements. So I will take something like this. The first element will be rewritten in this way. Second element will be rewritten in this way, and so on. And you see that the number of elements, as I replace 1 by 3, 1 by 3, 1 by 4, 1f by 4f, it's really growing in an exponential manner. So you see that the length of the string is really getting very huge very rapidly. Okay, and this you have in example 3. So go to example 3 and try to produce this figure and see whether it's easy for you now or it's not. So it's easy in a way once you have really understood the stuff. So you see here, I have the curve that I had before. I have 3 times. 1 time here, 1 time here, and 1 time here. So in order to get this in the end, I just need to compose in the beginning an axiom made of an equilateral triangle. Okay, and then I will apply the rule to this equilateral triangle, and this will give this snowflake, one-core snowflake. And the axiom in the beginning, the rule with an f, I think. So it will be f of 1 plus, because equilateral triangle would be 60 degrees, plus 60, f of 1. No, it's not plus 60, sorry. It's this way, plus 120. F of 1 plus 120, f of 1. Yes, because when you want to make a equilateral triangle, you need to instruct the turtle to turn. When she gets here, the heading vector is in this direction, and I need to instruct to turn here. So the angle that I must make is 120 here, and not 60 as I said initially. Yes, it's minus. So if you turn in this direction, it's minus, and if you turn in the other direction, but it will make the same. Sorry?
If we have the wrong direction, it will make the figure inward.
In the other direction, yes. Okay, now we get to slowly to more complicated examples. If we want to put a bit of randomness in the system, it would be rather easy. We need to use the random facilities that are embedded in Python. And then I will try to walk in order to create a walk that changes the heading direction every now and then. Just a syntactic new thing. When we used to write A of n produce A of n, f of 0 A of n, let's say. Now, to construct more complex production rules, we can use another syntax, which is like this. A of n, well, it's not produced, but becomes. And now I can write Python code here. Plus LPy instructions. So for instance, the LPy instruction that is not included in the Python language is this nProduce, which actually stands for this arrow. So for instance here, it's A equals something, nProduce something plus A, and then you have it could be like to be equivalent to what is here, it would be f of 0, A of n.
What's the difference between produce and nProduce?
Produce will get out of the rule as soon as it is encountered, and nProduce will not get out of the rule. N meaning multiple. So if I write, I can write a rule like this, A of n, nProduce this rule. I rewrite it in this way, nProduce f of 0, nProduce A of n. I construct my output in several steps. Okay. If I had used produce instead, I would never get to this instruction because this will return before I get to this instruction. So nProduce is when you want to construct your output step by step.
Okay.
Okay?
And what's the at?
Which one? And this one is the instruction for the turtle to draw a sphere. So at sphere and the radius of the sphere. Yes, progressively I will introduce a bit more complex. They are equivalent. You can see in the help card. They are full letter equivalent of these bizarre instructions. I think for sphere would be sphere. So it's a bit easier to remember. Okay. So did you try this example 4? And you see that we start to obtain a quite complex behavior, still based on a very simple program. And you see that the structure of the program basically has not changed. It's a recursive rule. The A keeps on being an A, possibly by changing its own variable, and produces on the fly some Fs. And the Fs are the steps that are being traced on the screen. Any question on this example? No? Okay, let's go on. Now, there will be the problem of turtle interpretation of brackets. And this is one of the important aspects of being able for the turtle to plot branching systems. When the point is that the turtle will interpret this, and you see here that there are brackets. And owing to these brackets, it will be possible to create this bifurcation here. This point occurs exactly at this point. So how it goes? Internally, the turtle, when she's reading the string, has a state. And there are many things in the state, but the most important things are the position of the turtle, where she is in the space, the HLU frame, what are the orientation of H, of L, and L of U, and a number of things like the color of the turtle, the material, etc. The turtle will do, this is thanks to this state that the turtle is able to make the next move forward, because she knows the HLU, she knows the XYZ, so she knows how to interpret an F from the previous position. Okay? Now, in order to make this branching system, the turtle will interpret the brackets in the following way. She has a state at a point I of the system. She has a state Si, which is the position, the HLU. And then she reads this. Assume that at this point she has this state. So what will occur is that the turtle will push the current state when she encounters the bracket. She will push this state on the stack before going proceeding further in the string. And look, the idea is that if I push, it's like I sort of record my position for further use. Then I can use this and change my state, whatever. And when I encounter the bracket, I will restore the state that I was pushing on my stack. Okay? And in this way, I can accumulate as many branches as I want. I will be able to each time recover my state in a consistent manner. So I can just show you how it works. So when you read the first character, you are the stack state of the turtle. Sorry, the state of the turtle is S1. You read the second F, the state is S2. And then I encounter this, my state is still S2, and I push this on the stack, which start to fill in my turtle stack. Then I continue, and you see that at the level 1 of the stack, I keep track of my previous state, but I can change my current state and read this without any effect on this. And then thanks to this, I can change my state during my parenthesis. And then once I encounter this close bracket, I will restore my previous state and then resume at the position before the bracket. Okay? So this is very smart and very used mechanism in computer science to do many algorithms on trees or on graphs. But for the turtle is quite efficient and very, very useful to keep track of shape and geometries. Okay, so let's try to draw a first branching structure. And then I think we will stop at this point after that because I see it's already, well, we can see. If we stop at 6, it will be okay for everybody? Yeah? Not too tired at the moment? Okay, so let's try to make the first branching structure. So the first branching structure will have this rule, which is an A followed by that is producing an F and 2 lateral A's. Okay? So you see that the F will produce this, and the plus will orient the head in this direction, but with a bracket. And the other minus will orient the turtle in the other direction with a bracket. And the A. Okay, so I make a F, and then I point in 2 opposite directions at the head, at the tip of the F. So what will occur when you do this? The A will be rewritten, and each A will in turn will be rewritten. And the parts that are not rewritten are kept the same. Like for instance, the F square bracket and plus will keep F square bracket and plus because they are not rewritten. And only the A that corresponds to this rule will be rewritten in the red part here. And then the string continues. So you start. So as I said, this will be the geometric interpretation of this. In the beginning, we'll start to have, after the first derivation, so this part will be interpreted as this. There is no way to, for the turtle, A doesn't mean anything, so it doesn't interpret it. So what we only see is the F here. And after the second derivation here, what we have is one F, and then plus a F on the left and plus a F on the right, and then the 2 A's here that are not visible on the drawing. And then if I continue this, you see that it will produce a structure like this, reminiscent of a dichotomic branching that we saw this morning. Okay, and this is in example 5. You can open the example and see how it goes. It's basically the same. You can try to introduce like a third branch, maybe, at each node to see how it goes. Try to change a bit the angle. I mean, try to play a bit with it so that you start to make up your mind about how the system is behaving. Okay. There are, because there are a couple of slides left, and it would be nice to finish this. I think by 6 we are finished. there are a number of modules that makes it possible to retrieve the state of the turtle. And this is how it goes. You have the string, and at some point you want the position of the turtle. So there is a special module that is $P. And if you put this module here with whatever values, it's not significant here, you will retrieve, when you apply the rule, the turtle will send in this module back the actual value of the position of its position. So it's a way to question the turtle, where are you at the moment? And then it will answer. When the turtle will read the L string, it will modify the module and give the answer. I am at position 0, 0.7, and 2.707. And you can go to example 6 of the 6 family here to see this, how it works. So you see the turtle was able to go up to here. So the frame is at this point, the state is at this point. Here you ask, what is your position? And then when the turtle reads the string, it will rewrite this part with the actual position of the frame here. And you can do this, and this is why there are different examples here, with the position, with the head, which is a vector of the turtle, with the left and the U, and with all the frame components at once, using the $F. So this will be used, for instance, when we are going to, if you want to see how a model is interacting with the environment. Like, for instance, if a plant would be growing in a soil, then you would need to use this type of modules in order to get the position of the turtle and then to seek in the soil model what is happening at the place of the turtle at this moment. So important for when you have this type of models where you have interaction between the geometry of the system that you are constructing and the geometry or what is happening in the environment. Okay? Finally, and this will finish the day, one important aspect of all this is that we don't want to merge the geometry and the topology. Actually, since the beginning, you see here, I'm always mixing things. F is an instruction for the turtle to move somewhere, and A has no meaning. So what is very important is to separate what is part of the model. Sorry, because this is not well animated. What is part of the model and what is part of the geometric interpretation, which is less relevant to the modeling. For this, instead of, for instance, I took the example of a circle. I have a production that mixes both things. That the model says that an apex, let's say, produces an instruction to make a step forward, and then an apex. And then this produces this, and this produces the circle. One way to get rid of this confusion between the geometry and what I want to say in the model is to abstract from the geometry. So I write exactly the same thing, but instead of using the F here, I will use any other symbol that is not meaningful for the turtle. And then, in my head, this corresponds to an abstraction of what is a circle. Okay? I don't know that S will be interpreted as an F. It may be interpreted as an F, maybe not, maybe by other things. And if I want to do this, you see that there is a need to separate two types of rules. The rules that will be used for the progression of the model itself, and the rules that would be used for the interpretation of the model, this type of rule. S, what is an S? An S is an F, sorry, it shouldn't be A here. You You can remove this. Sorry, it was a bit. The rules should be like this. A gives SA, so this would be one production rule, and then there would be an interpretation rule, which would mean S is a F, should be interpreted as a F. Okay, so this would produce a list of S when I apply derivations, and then if I reread now this part and I interpret this with this other type of interpretation of rules that is called interpretation rules, I transform this as F, 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 F. And then I have separated the inner part of the system which has no geometric meaning with the outer part of the system which could be interpreted by the turtle. Okay? And it's a design pattern when you want to keep separate the geometry, what you want to draw, and what actually you want to say about the model. And this is the way, for instance, here, in example 7, by just using this and changing this rule, okay, if I put this rule here, I obtain this. If I put a rule that would say S gives, should be interpreted as plus F minus F, actually it is written over there, instead of this, then I can draw whatever I want at the position of the turtle here. Okay? It's the same production rule, but different. So you see that they are different. Remove the A here, they are not correct. Same production rule, different interpretation rule, provides with the same hidden model, the same deep model, provide different types of surface output. Okay? Okay, and this is the final, I think the finals. Okay, we can end here. I propose that we end here. There are just a couple of slides, and actually this would be a good way a good point to start from tomorrow, because this would be a recap for Fabrice as well. Okay, thank you very much.
Thank you.